Welcome to lecture number 20. My name is Professor J.N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. This Module 5, Lecture 20, Geosynthetics in Pavement. The outline of this course: introduction, mechanism and concept of pavement, design of unpaved road, design chart of US Forest Service USFS for unpaved road, modified California bearing ratio CBR test, design of pavement in unreinforced and reinforced condition, development of design methods for geosynthetics reinforced flexible airfield pavement, pavement overlay, geosynthetics in railroad, geosynthetics in roadway repair and extension, and stabilization of pavement using nanomaterials. As you know that basic concept is soil mechanics and the polymer material. You should know what should be the characteristics of the soil as well as what is the characteristics of the polymer material. Then interaction between the soil and the polymer material will ensure you the defined types of the application. So, it may be soft soil application and reinforced field application. Soft soil application is unpaved road, embankment, which is short term reinforcement strength required. And this reinforced field application is steep slope and retaining wall, and this for the long term reinforcement strength requirement. So, here that short term reinforcement strength required and long term reinforcement strength required depending upon the type of the application. In case of the pavement or the temporary infrastructure, the short term time is generally 5 to 25 years. If it is a long term, it is generally 50 to 100 years and 70 years for the retaining wall and 100 years for the abutment. Here we will concentrate mainly on the road. So, we will discuss that how we can design the road, and this particular application of the road that triggered the acceptance and application in the early of 1970s, and we will check that what will be the cost of the aggregate lost and what will be the cost of the geosynthetics material, and we will be able to tell how much percentage of saving using this geosynthetics material. At the same time, it is very important to realize that the geosynthetics must have its very good tensile modulus or the strength mobilized via the deformation of the soil subgrade material. Road and highway are the backbone of any country in the world for development. India has the second largest road network and fastest growing airport infrastructure. Indian Railway has a network of 63,465 route kilometers. Rut formation under heavy vehicle load is a major concern for unpaved road over soft subgrade. It is required to minimize the rut formation to prevent the local shear failure. It can be achieved by increasing the thickness of the base layer with good quality of fill material. In that case, the ground pressure on subgrade gets reduced due to wider load distribution. However, it will increase the cost of construction. The subgrade soil can also be improved by stabilization system using lime, cement and chemical. This will also lead to a higher construction cost. So, placement of geosynthetics over subgrade soil can substantially reduce the required fill thickness. It can provide the following benefit. It acts as a separation layer, reduce the vertical and lateral deformation, reduce construction and operational cost, increase the bearing capacity of subsoil, increase lifetime of the road, better drainage, rapid consolidation, less periodical maintenance and saving of the construction cost. Generally, geotextile and geogrid and combination of geotextile and geogrid are used in the pavement. Hybrid geosynthetics can be used as a good drainage, filtration and reinforcement material. So, it acts as a both reinforcement as well as drainage and the filtration, because it is a combination of geogrid and other woven or non-woven geotextile material. So, geogrid can take care as a reinforcement function, whereas the woven and non-woven geotextile material can take care as a filtration or drainage function. Geosynthetics should properly be selected, specified and installed. Use of geosynthetics ensured 36% improvement in highway quality and 10% saving in cost. The beauty of geosynthetics is that it not only acts for separation, but also acts for the filtration, drainage and reinforcement. That is why it is called multifunctional. Now, in general, that what are the benefit you can obtain in terms of the functional concept. For example, that it separate the coarser material and the finer material. That means it reduce the intensity of the stress on the subgrade and also pavement stone penetrating into the subgrade. So, it can reduce. So, it acts as a separation. So, this is the benefit in terms of the functional aspect. Then also as a reinforcement as well as the filtration aspect, that it can prevent the subgrade fine from the pumping or migrating up into the base course. So that here the benefit in terms of the separation and the filtration. Also it comes the benefit in terms of the filtration. Suppose it can prevent the contamination of the base material of the open graded from the drainage to be considered into the design. It also acts as a separation and reinforcement function, and it can reduce the depth of the excavation. You do not require the too much of the excavation of the soil. So it can reduce, and you can remove only the unsuitable material from the site, and then you can place the geosynthetic material. It can also reduce the thickness of the aggregate. So thickness of the aggregate material also can be reduced drastically, and reduce the differential settlement of the road, which will here geosynthetic material act as a reinforcement, and also it can reduce the maintenance and the extend the life of the pavement. So these are the some of the benefit in terms of the functional aspect. Now let us look at what is the mechanism and concept of pavement. Now here you can see that this is a fine grained material, this is the stone aggregate. So this stone aggregate enter into the fine subgrade soil and lose its strength. As you know that stone is very good material for the improvement of the bearing capacity. Now this stone aggregate get lost into the finer grained soil. So what geosynthetics can help you? Now sometimes you can see there is a excess pore water pressure in the fine grained soil, and soil pump into the void of the stone aggregate, causing the stone aggregate to lose its drainage capacity. And at the same time you know that stone is very good drainage material, and this also get lost and it clogged when the fine material enter into the void of the good quality of the aggregate. Now what is role of the geosynthetic material? Now if you can introduce a layer of geosynthetic material in between the finer grained soil and the stone aggregate. So here this geosynthetic material act as a separation. So geosynthetics prevent the granular material from penetrating into the soft underlying subgrade, as well as prevent fine grained subgrade soil from being pumped or migrated up into the permeable granular material. So geosynthetic may tear up due to the sharp edge grain of the ballast under the dynamic load of railway. Therefore sandy gravel as a protective layer is placed under the ballast where there is a dynamic load, so it will act as a cushion. Now in this slide shows that how the geosynthetic material act as a filtration, act as a drainage, and also act as a reinforcement. So here is the aggregate, that is aggregate try to move downward into the soft subgrade soil, and the water from the soft subgrade soil pumping upward, or the water can migrate it this upward into the void of the stone aggregate due to the wheel load. Now, water also at the same time drained it out from the subgrade soil. So, when you place the geosynthetic material, so when the water may move up from fine grains to the coarser material, or any rain water which comes to the coarse aggregate can enter into the soft subgrade material, where this geosynthetic material act as a filtration. Also, the water move from fine grains to the coarser grain, or coarser grain to the finer grain, and water can pass along the plane of the geosynthetic material. So, here this geosynthetic material act as a drainage. So, you can see that geosynthetic material act as a filtration, and at the same time geosynthetic material act as a drainage. And also this geosynthetic material which separate the coarser and the finer material, and that is why the geosynthetic material act as a separation. Also, due to the load, there is a deformation of the geosynthetic material, and then also geosynthetic material will act as a reinforcement. So, all this function will do at a time, and that is called the multifunction. Now, mechanism of reinforcement. As you know, soil good in compression and poor in tension. Geosynthetic good in tension but poor in compression. So, combination of geosynthetics and soil ensure an excellent bond and form a composite material. Now, when you will design the geosynthetic reinforced pavement, and it is based on the three main reinforcement mechanism. This is very important to us. What are those three main reinforcement mechanism? The one mechanism is the lateral restrain, second is bearing capacity, and third is the tension membrane. Now, what is lateral restrain? You can see here, this is the dot line is the geosynthetic material. This is geosynthetic material. So, you can say lateral restrain, that when we apply the load, then aggregate will try to move outward. So, there will be a mobilization of friction and or interlocking between the base or subgrade course and the geosynthetic material. So, aggregate will push outward, and geosynthetic material which provide the lateral restraint. So, that is why this is the lateral restraint of the geosynthetic material in shown in arrow here, similarly on the right hand side. So, due to the wheel load, there is a mobilization of friction, or if it is a geogrid material, there will be interlocking or bonding between the base course and the subgrade course and the geosynthetic material. So, that is the why that lateral restraint mechanism is important to us. Next, bearing capacity. So, you can see this is the wheel load, and this is the geosynthetic material is placed. Due to geosynthetics, the failure zone possesses the higher volume and hence increase the bearing capacity. You see in the conventional or the probable bearing failure without geosynthetics, you know it is passing like this. This is the probable bearing failure without geosynthetics, like this dot line. On the other hand, if you provide with the geosynthetic material, then this is the hypothetical bearing failure with geosynthetics. You can see it is like this and it is like this. That means there is an increase in the bearing capacity because geosynthetics failure zone passes higher volume. It passes higher volume with respect to probable bearing failure without geosynthetic material, and that is the reason that why the bearing capacity has been substantially improved due to the presence of geosynthetic material. So this is the second mechanism, that how the geosynthetic material can improve for bearing capacity. Now third, tension membrane. So you can see if we apply the wheel load and then there will be the development of tension. This is the geosynthetic material, you apply wheel load, there is a development of tension. Let us say the tension is T in the geosynthetic material due to wheel load resulted in a vertical thrust. There is a upward pressure from the geosynthetic material. So when there is no reinforcement, the entire thing may go down. On the other hand, if we can provide with the one layer of geosynthetic material, so there will be the upward pressure from the geosynthetics and there will be development of tension, both the side tension, and at the same time there is a formation of rut. So rut will form. So we have to check that how we can minimize the rut. So these are the three basic mechanisms of the geosynthetics for the unpaved road. I mentioned that there is a lateral restrain, there is a improvement of the bearing capacity, and also there is a development of tension membrane. That means tensile strength of the geosynthetic material is very important to us. What should be the modulus of the geosynthetic material? That is very important to us. Now you can see some figure that what are the kind of the problem in the unpaved road. You can see it is very difficult. This is a formation of the rod, very difficult to move any vehicle. You can see water also is stagnant, very difficult to move. You can see some unpaved road, and if you do not provide with the geosynthetic material, then you cannot control the car. So there are various applications. It may be for temporary roadway, haul road, access road, permanent road, airport taxiway, railway track, parking lot, etc. So what type of geosynthetic material used in the pavement? It may be woven and non-woven geotextile material, extruded geogrid, polypropylene, polyethylene, welded geogrid, polyester, polypropylene, polyethylene, knitted or woven geogrid, polyester, polypropylene, bonded geogrid, geotextile, composite, that means geogrid and geotextile as a composite material, where geogrid will act as an reinforcement and geotextile will act as a filtration or drainage. Unbonded geogrid, geotextile composite, that is geogrid is laid over geotextile material. Now, what will be the type of the subgrade? It may be the firm subgrade if the California bearing ratio or CBR greater than equal to 8 and shear strength value greater than equal to 240 kilopascal and resilient modulus is greater than 80 megapascal MPa. Number 2, if it is a moderate subgrade, that means when the CBR is greater than equal to 3 but less than equal to 8, then shear strength lies between 90 kilopascal and 240 kilopascal and resilience modulus lies between 30 megapascal and 80 megapascal. Number 3, low subgrade. If CBR less than equal to 3, then shear strength less than equal to 90 kilopascal and resilience modulus less than 30 megapascal. These are the some kind of the subgrade condition. So, subgrade condition for unpaved road generally should lie within this range. It should not be some CBR value much higher. Then maybe geosynthetic material has no role. But if it is a very soft soil, where CBR value less than equal to 3 or CBR value greater than equal to 3 or less than equal to 8 or certain extent CBR value greater than is equal to 8 is reasonable, and then you can apply this geosynthetic material for improvement. Now, design of geosynthetic reinforced pavement require an overall knowledge of the following area: unreinforced pavement design, reinforced pavement design, life cycle cost analysis, value added cost benefit, specification, product specification of generic material property specification, 20 to 50% sub base or base course thickness reduction, maximum 75 to 125 millimeter is used. Design of unpaved road. Giroud and Norway 1981 developed an analytical method for designing the geotextile reinforced unpaved road on soft subgrade soil, and he assumed the following step, that is soil subgrade is saturated, fine grain, clay and silt. So, it is a saturated soil, that tau is equal to the C, shear strength is equal to the cohesion value, and soil subgrade is under undrained condition. So, no drain condition. Shear strength of the soil subgrade is represented by the cohesion only, no angle of internal friction. The bearing pressure can be transferred to the elastic limit range for unreinforced soil, and the bearing pressure can be transferred to the plastic limit range for reinforced soil, and the wheel pressure transferred like a pyramidal shape. So, before that I just wanted to show that what is the happening if it is an unpaved road and is defined without geosynthetic material. So, if this is the aggregate and thickness is equal to T0. This is unpaved road as it is designed without any geosynthetic material. Let us say this thickness is T0. And now some same road when after a few weeks or the month. So, what will happen? The some parts of the aggregate penetrated into the subgrade soil. So, you can see here some aggregate penetrated into the subgrade soil. So, this thickness if I say T1 and this thickness if I say T2. So, this T1 is the effective useful base course thickness is much less than this T0, that is required design thickness. So, this is the effective useful base course T1 is the effective useful base course thickness is much less than the T0 that required design thickness. So, now if you provide a reinforcement in between, so if we place a one layer of the reinforcement or geosynthetic material here, so this is your textile, this is your textile material, you can say geotextile material, and then this thickness is T0 is equal to T1. That means aggregate intact even after the considerable use, because the pressure of the geotextile, then T1 is equal to T of 0. So, this is the wheel load distribution without geotextile, that is on the left, and with geotextile on the right. This is reported by Giroud and Norrie in 1981. Now, here we consider this is as a shallow foundation theory of the geotechnical engineering can be utilized. Now, this is the geometric model is given by Giroud and Norrie. This is without geotextile material. Now, this tire wheel load of pressure PEC, tire wheel load of the pressure PEC on the area, that is B, this is B and the L. So, tar wheel load on the pressure on the area, B is the width of the tar, L is equal to length of the tar. So, B into L area which dissipated through the thickness of the aggregate base without geosynthetic material at an angle alpha 0. So, this is pyramidal geometric shape due to the load spreading. So, due to the load spreading, you can see how it is pyramidal geometric shape, formation of pyramidal geometric shape. And in unenforced case, it is making at an angle of alpha 0. So, here H0 is the thickness of the base course without geotextile material, and stress is P0 and this height is H0, gamma is the unit weight of the aggregate. So, this will be gamma into H0. So, you can see that how the stress has been distributed. Here it is A0 dash to B0 dash, then after the application of the load, and it is A0 to B0 and this is 2 of A0. Now, this is the pyramidal geometric shape when there is no geosynthetic material. Now, right hand side when the geosynthetic material has been introduced. Now, same that tar wheel load of pressure PEC on the area B into L area which is dissipated through the aggregate base course with the geosynthetic material, and it is making an angle of alpha, and here H is equal to the thickness of the aggregate base course. Here it is H0 unreinforced case and here it is H in the reinforced case, and gamma is the unit weight of the aggregate. So, here this will be gamma into H. So, in case of with geotextile, this is A dash into B dash and this is A into B, and this distance is equal to 2 into A. So, this is the basic concept and mechanism which is given by the Giroud and Norway, and based on this concept and mechanism, he has developed an equation, and from that equation we will show how you can make the design chart for without and with geosynthetic material. Now, equivalent tar contact pressure, that is PEC. PEC is equal P divided by 2 into LB. P is the axial load. So, wheel load will be P by 2. So, that is why the equivalent tar contact pressure PEC is equal to P by 2 into LB. As I say, B into L is the contact area of the wheel. This is B into L is contact area of the wheel. This is width of the tar and this is length of the tar. So, this contact area of the wheel will be B into L. So, equivalent tar contact pressure PEC is equal to P by 2 LB. Now, without geotextile, you can write PEC into L into B is equal to B plus twice H0 tan alpha 0, L plus twice H0 tan alpha 0, P0 minus gamma into H0. as I say, H0 is equal to aggregate thickness without geosynthetics, and alpha 0 is the angle of load distribution, that is 45 degree minus pi by 2 or 26 degree, and this P0 is the stress on the soil subgrade without geotextile, and gamma is the unit weight of the aggregate, and P0 is the stress on the soil subgrade without geosynthetics. Here P0 is the soil subgrade without geosynthetics, here P0. Okay. So, this is the B, I am explaining you. P into EC into LB, that means PEC into this area, B into L, will be equal to B plus twice H0 tan alpha 0. This is B, this is B, and this point, you can see this is the H0, from here to here H0, this angle is alpha 0. So, this will be H0, this will be H0 tan alpha 0. Similarly, this side H0 tan alpha 0. So, it will be the 2 H0 tan alpha 0. So, that means this B plus 2 H0 tan alpha 0. So, that is why 2 H0 tan alpha 0. Similarly, L plus 2 H0 tan alpha 0. You can see this is the L, this side is the L. So, this will be L plus 2 H0 tan alpha 0. That is why L plus 2 H0 tan alpha 0. And here is, this is the P0, the stress is P0. So, P0 minus gamma of H0. So, then this will be P0 minus gamma H0. That means P into LB after the dissipate, then it will be equal to B plus twice H0 tan alpha 0, L plus twice H0 tan alpha 0 into P0 minus gamma H0. This is P0, this is gamma H0. So, this will be P0 minus gamma H0 here. So, this is without geosynthetics material. So, you can obtain this equation. Now, with geotextile material, this equation will be on the right hand side, PEC into B into L, that is the area, will be equal to, similarly this angle is alpha. So, this area will be B plus twice H tan alpha into this side is the L, L plus twice H tan alpha, B plus twice H tan alpha into L plus twice H tan alpha, and this is P. So, P, and this is gamma H, that is P minus gamma H. So, this will be equal to P minus gamma H. So, with geotextile material, PEC into LB equal to B plus twice H tan alpha, L plus twice H tan alpha, P minus gamma H. You know, here H is equal to aggregate thickness with geotextile material, and alpha is the angle of load distribution with geotextile material, and assumed to be equal to alpha of 0, and P is the stress on the soil subgrade with geotextile. This is P is the stress on the soil subgrade with geotextile. Here P0 is the stress on the soil subgrade without geotextile. Now, from the previous equation, so we can write the following equation, that what should be the stresses on the soil subgrade without geotextile, and what should be the stresses on the soil subgrade with geotextile. The stresses on the soil subgrade without geotextile is P0. So, P0 will be equal to P divided by 2 into B plus twice H0 into tan alpha 0 into L plus twice H0 tan alpha 0 plus gamma H0. So, you know this, and from this you have to determine what should be the P0. So, this P0, because you know this is PEC is equal to P by 2 LB. So, if you substitute this here P by 2 LB, so LB will be the cancel. So, this will be the P by 2. So, this you can write from here that P0 will be equal to P divided by 2 B plus 2H0 tan alpha 0 into L plus 2H0 tan alpha 0 plus gamma into H0. This is gamma into H0. Okay, you are substituting this PEC here, P by LB you know. Then from here you are calculating P H0. On that side then it will be the gamma of H0. So, this you are having the stress on the soil subgrade without geotextile material. Now, similarly stress on the soil subgrade with geotextile is P. So, P will be equal to P capital divided by 2 into B plus twice H tan alpha L plus twice H tan alpha into gamma of H. So, from this also you can determine. So, we know what will be the stress on the subgrade soil with and without geosynthetics. Now, unreinforced road, when there is no geotextile material, stress on the subgrade soil P0 should not exceed the elastic bearing capacity of the subgrade soil, that is QE. So, we can write that QE is equal to P0 is equal to pi into Cu plus gamma of H0, because we consider that shallow foundation theory of geotechnical engineering and we assume the soil is undrained condition and soil is saturated, fine grained soil, clay soil or clay silty soil, and also it is a compressibility of the foundation soil for unpaved road. So, without geosynthetic material, maximum pressure that can be maintained corresponding to the elastic limit of the soil. That means elastic limit, that means P0 will be equal to pi into C of U. So, elastic limit of the soil means P0 is pi into Cu plus gamma of H0. That means QE is equal to pi into Cu plus gamma H0. Now, what Cu is the undrained shear strength of the subgrade. Now, again that you can write that P0 will be equal to P divided by 2 into B plus twice H0 tan alpha 0 L plus twice H0 tan alpha 0 plus gamma of H0. So, from this and this equation, you have to calculate what is C of U. That means Cu will be equal to P divided by 2 pi, because pi is here. So, 2 pi into B plus twice H0 tan alpha 0 into L plus twice H0 tan alpha 0, and gamma H0 will be cancelled from both sides. So, from this and this equation you can calculate what is Cu. So, we are having the value of Cu. Now, that if it is a on highway vehicle, so L will be equal to B by root 2 and B is equal to P divided by PC. For off highway vehicle, L is equal to B by 2 or B is equal to root of P root 2 divided by PC. For on highway vehicle, Cu is equal to P divided by 2 pi root over P by PC, because that is the B, plus twice H0 tan alpha 0 plus root of P divided by 2 PC plus twice H0 tan alpha 0. If it is a for off highway vehicle, then Cu will be equal to P divided by 2 pi, then root of P root of 2 divided by Pe plus 2H0 tan alpha 0 into root of P and then root of 2Pe plus 2H0 tan alpha 0. Now, if you know that what is undrained shear strength of the subgrade, that means Cu, if you know that what will be the axial load P, if you know the tar pressure Pc, and the angle of load distribution alpha 0, that is 26 degree, the required theoretical thickness of the granular layer field H0 can be determined. And if the CBR value is known, you can calculate the what will be the undrained shear strength of the soil, that is Cu is equal to 30 into CBR percentage, that is kilonewton per meter square. So, remember that this is the undrained force case, how you can calculate the thickness of the pavement. So, this is the equation which we will adopt for the design of unpaved road without geosynthetic material, and also we will adopt that maximum pressure that can be maintained, that is should be within the elastic limit of the soil. But in case of the reinforcement where we will introduce the geosynthetic material, then limiting pressure can be increased to the ultimate bearing capacity of the soil. Then this equation will change, which we will discuss the later. So we should understand first of all that how to design the pavement without geosynthetic material and what should be the thickness of the pavement. So, first of all that you should know what will be the CBR value or the undrained shear strength of the soil, and at the same time you should know what will be the tar pressure, and then you can calculate that what should be the thickness of the granular layer field. With this I ended up this today's lecture. Let us hear from you any question, and thanks for listening.